Okay, so yesterday we kind of wrapped things up, or we didn't wrap things up. We were getting into intensity. We're just getting started with this. And we were talking about the intensity of sound, how that is your power in a certain amount of area. And we measure that in watt per meter squared. So you should have this. And then what we did is we looked at two variables that kind of regulate how much intensity you're going to have. And typically we associate the intensity of sound with loudness. So this is where the loudness stuff starts coming in. But anyway, those two factors that regulate how much intensity you have, we gave this to you yesterday as well. Your intensity is going to be inversely proportional to your area, or your distance squared. Okay, I gave this to you, correct? So this would be like having a concert in this little room. So if we had AC/DC, which could be, there's some good AC/DC, some not so good AC/DC. But if you went to a concert hall, to an AC/DC concert, the reason I said AC/DC is because it's a bunch of grown men screaming and yelling in microphones and screechy guitars. Really loud, can be annoying. So you go to a big concert hall and you listen to AC/DC, it's going to be loud, it's going to be intense, the sound level is going to be intense. But if we were to take that concert and move it into this room using the same equipment, same amount of speakers, we would walk out of here with ear damage and probably some brain damage too, partly from the loudness and also from just the music itself, okay? So, but it would be really, really loud because what we did is we took the area and we shrunk it. The D squared value is much smaller, the area in this room compared to a concert hall. And if they're inversely proportional, if the area goes down, the intensity is going to go way up. And then the other variable here was amplitude. And this is why people buy amps when they get a guitar. They want more sound. They want it to be louder. It's going to be more intense. So when you amplify, you increase your amplitude, you're going to increase your intensity also. And did we discuss how people used to do this with their car stereo systems as well? All right, and then cruise Main Street. So, but anyway, amplitude and area. Those are the two things that kind of regulate your intensity. Now, how do we interpret this intensity? Well, we consider this to be loudness. So how do we measure that loudness, that intensity level of sound? We use decibels, and you guys have probably heard of decibels before, but you may not understand exactly how the decibel scale works. First of all, it is, okay, I guess I got some values here that go with it before we get into the scale, but this is our common unit of intensity for sound. The threshold of hearing here is usually 0 decibels. That's when you begin to hear sounds. Remember in the video clip, they referred to that anechoic chamber. I did show you that too, didn't I? Anechoic chamber. That records negative decibels. So when you begin to hear certain sounds, that's usually because they're at a decibel level of around 0. And then the higher you go, the more intense those sounds are going to be. Now, what I don't want you to assume is that if I have something that's 20 decibels, and then the next sound that you hear is 40 decibels, most people think, oh, 20 and 40, it's twice as loud. It is not. That's not how the scale works. Or 50 and 100, the 100 is twice as loud as the 50. It does not work that way. All right, it's actually a logarithmic scale. So calculating it's a little tricky. Once we show you the trick, it's a piece of cake. Now in terms of decibels here, when you get up to 120, this is when it physically starts to hurt your ears. All right, when you get it to about 120 decibels, like if you go to a shooting range and you shoot a gun, you could get up to 120 decibels easily and hurt your ears. It could physically hurt. Airports, you know, those guys working out on the tarmac, they always have headsets on because that decibel level is going to be clear up to around 120, 150. It's going to be really, really loud, and it's going to be painful. It will physically cause pain. All right, so our decibel scale is logarithmic. What's that mean? Should have done this. You did You're making comments already. It's because we said logarithmic. You're like, I hate logarithms. I hate it in math class, right? You can all say it. I agree. I agree. Logarithms aren't fun. But there's an easy way to calculate this logarithm. Okay, this one is not very difficult. Just to kind of give you this basic understanding of your logs, though, they're usually based on the power of 10. Right? That's what logarithms are. So for every 10 decibel increase that we experience, that's actually an increase of intensity of 10 times. So if I go from 20 to 40, like we said before, okay, most people think, oh, that's twice as loud. Not even close. All right? To go from 20 to 30, that's a 10 decibel increase. That's 10 times. And then when you go from 30 to 40, that's another 10 times. So it's not twice as loud, it's actually 100 times as loud. 20 to 40 is 100 times as loud in terms of intensity. So people kind of miss the boat here in terms of reading the decibel scale. All right, so here's the formula. Here's how you're going to use it. It's way easier than any of your logarithms that you used in math class. It's 10, and then your exponent here. How to determine your exponent? It's 10 to the power of whatever the difference is in your two decibels. So I'll use the 20 and the 40 since that's what I was using before. I go from 20 decibels to 40. The difference is 20, right? 40 minus 20. Then you take that difference, you divide it by 10, which is 2, and that becomes your exponent. So this is 10 squared, which is 100. That's how we come up with this. Every 10 decibel increase is 10 times. It's really easy. So we don't really get into the in-depth, complicated process of using all your logarithm stuff. This is much easier. So this is your main equation for calculating intensity of sound, your decibels. Your exponent is the difference divided by 10, and then that's 10 to that power. And I got another example here in a little bit that we can solve. So, any questions on decibels? Intensity? All right, here's a few examples. Oh, not that. Let's skip it. This is what I wanted to go to. Of different sounds and where they fall on the decibel scale, just to kind of give us a reference. So some of these are really bad. I don't get, like wilderness. Wilderness is 20 decibels. I don't know if that means you go out into the woods and just sit down for a little bit and just listen to the nature. All right, so evidently wilderness is 20 decibels. Is that like the howling coyotes or something? Or I don't know. Rustling leaves. So like in the fall when the leaves are blowing across your yard and stuff, when it's windy, 40 decibels. Rain, a typical rainfall. You go outside and just listen to the rain, 50 decibels. A normal conversation, 60 decibels. So you're sitting at lunch, it might be a little louder at lunch, all right, but a normal conversation that you have with somebody, talking in the hallway, 60 decibels. Normal traffic. So you go out Main Street on a normal weekday, you're talking about 85 decibels. Chainsaw. Now you're getting up there, 100 decibels. Not to the point of the pain of threshold, but enough where you'd probably want ear protection. And if you were exposed to 100 decibels all the time, if you're a logger, lumberjack, you're probably going to want to use ear protection because you're exposed to this all the time. A rock concert, 110 decibels. And then here you get to, a jet plane, you're at 130, okay? Minimum 130. So you kind of get an idea of how the scale works. All right, any questions on intensity, different examples of decibels. Good? All right. So loudness then is kind of our human interpretation. So decibels are an actual measurement. There's equipment that can measure your decibel level. Okay, we can actually figure out what that exact value is. Now, loudness, on the other hand, is kind of like pitch. Remember, yesterday we said that pitch was the human interpretation of frequency. So when I strike a tuning fork and I ask you for what's the frequency, you can give me values of the frequency that you think you hear, but there's an exact number. Okay, so if you tell me, that's 200 hertz, that's 300 hertz, well, you're both wrong. Okay, you're wrong, it's 256 hertz. There's an exact value printed on there. Now, if I ask you for the pitch, and you say high pitch and someone else says low pitch, I can't really say one of you is right and one is wrong, unless I'm comparing it to another tuning fork. Then there's clearly a higher pitch and a lower pitch. But in that case, I can't really say one's right and one's wrong because it's a human interpretation. Loudness is kind of the same thing. It's a human interpretation. Anybody have a grandma or grandpa that every time you go over to their house and they're watching television, it's like blaring? As soon as you pull into the driveway, you can hear grandpa's television. It's like, Grandpa, turn the hearing aid up a little bit, and then turn the volume down. I didn't even put my hearing aid in, and that's why it's like blasting. The volume's way up. My kids do this all the time. It's always loud. And if you ask them, that's not loud, to me it's like blaring. Again, it's a human interpretation here of intensity. What one person thinks is loud is not loud to someone else. All you have to do is just watch students walk by my room with their earbuds in. I can hear their music. I think that's loud. This isn't loud. Okay. So, but again, it's a human interpretation. And this too will probably vary with age. Your ability to hear things is going to fluctuate. Again, we're not talking about selective hearing here. That's different. Guys, we're good at that, selective hearing. You really improve those skills when you get married too, just so you know. The filter becomes, the little girls are looking at me, he's such a jerk. Is that true? See, that's selective hearing. No, I heard it. So, do you guys have selective hearing? Does your dad have selective hearing? Your brothers do? Yeah, I can see that, especially Lou. All right, where am I at here? So, for us, for every factor of 10 increase in intensity, humans actually only perceive this as a factor of 2 in loudness. So when we go from like 10 to 20 on the decibel scale, we kind of interpret that as being twice as loud. That's why we often misinterpret the decibel scale, because that's how we hear it. That's how our ears pick it up. But that actual piece of equipment that is measuring the decibel scale can detect that. It's a little more sensitive in terms of measuring the actual intensity. Our ears aren't that good. I mean, they're good, but they're not as good as that equipment that's actually measuring the decibel level. So we only perceive it as a factor of 2. All right. The last, let's see, there's 1, 2. There's 4 terms here. That's the main thing we want to do, is just kind of define these terms. And then there's a couple in there where there's sample problems that go along with these terms. They're not what I would call major items that are going to be included in WebAssign or even on your test, but these are minor things that may show up on your test. There might be a question or two about these. So that's why I just want to cover them real quick, but I'm not going to spend a lot of time on them. except the last one, which is the Doppler effect. We have something called forced vibration. I don't want to get into this too much, and you don't even have to write down this part, but forced vibration is when, it's just what it says, when you have one vibrating object that's placed in direct contact with another, and then when you do that, you cause the second object to vibrate with the same frequency as the first. This is like taking a tuning fork, striking the tuning fork, and then putting it near the water. Well, what you're going to do is you're going to cause the water to vibrate at the same rate as the tuning fork. And that would be forced vibration. You're forcing the rate of vibration from one object onto another. So the second object will vibrate with the same frequency. All right, so right now, again, back to the tuning forks. When I strike my tuning fork, and then I would touch water with that, the sound energy in that wave is going to be transferred into the water, and so the water is going to generate waves with the same frequency as the tuning fork. So you're just forcing that vibration onto another object. That's all this really means. So don't get too caught up on forced vibration. I just want you to know what it is. So if you hit a question on your test, you know what we're talking about. So forced vibration does this or that. Sometimes they use this as just part of the wording in a story problem, so now you know what they're referring to. Now, you musical people, band people, there's like musical application with this and forced vibration. Sounding boards, boxes on musical instruments, or guitar. What's the purpose of the box on the guitar? Why don't we just pluck strings? What's that? Yeah, you're forcing the vibration of the strings through the air into the box, basically, which is kind of amplifying the sound, and you're forcing well, that's kind of the result. The amplification is the result of forcing all those air particles inside the box to vibrate as well. I think I've got one here, and you can clearly hear the difference in these. All right, this, I think it's the same one. 256. All right. So here's a tuning fork that's also 256 hertz, but you'll notice that it's on a box. So when I strike this, they look different, but they're going to produce the same frequencies. They both vibrate at the same rate. So I hit this 256 hertz. Okay. And then I hit this 256 hertz. You kind of get those overtones, and we haven't really talked about overtones yet, but it's louder. You're forcing the vibration from the tuning fork onto the wood box, because you can even feel the wood box vibrating, and you're forcing it through the air in here. So that forced vibration goes into the sounding box, makes it a little more intense. Lasts longer too. Bloody ears. Just kidding. We can do all kinds of torture with sound in here. Physics torture. I'm old, so if I damage my ears, it doesn't matter. So I can't hear anyway. All right, that's annoying. So guitars, pianos, just some examples here. Plucking a guitar string, piano, tuning forks. All different examples of forced vibration. All right. So that's one, right? One of the four, forced vibration. The next one here is natural frequency. So all these tuning forks have a frequency printed right on them. So when you hit them with the rubber mallet, they will vibrate naturally. based on the type of material, the shape. So they all have what we call a natural frequency. It's the frequency produced when an object is disturbed. When you strike it and it starts vibrating, it vibrates at a set rate. It gives off a certain number of waves per second. That's called your natural frequency. And a lot of factors go into the natural frequency. I mentioned some of those: size, shape, and even the stretchiness or the elasticity of the material can affect that natural frequency. And you're going to use these natural frequencies in your labs. So when you do your speed of sound lab, it'll be the second one. When you do resonance, okay, you're going to have to use the printed values on there. You're going to use the natural frequencies. So, and I think they have you vary it because you do multiple trials. So you'll use a 256 tuning fork, and then you'll change it to another natural frequency. And you'll notice that as the frequencies change, the size of the tuning fork usually changes as well. All right, resonance. I'm not going to spend a lot of time on resonance. I give you a reference here. You may want to jot that down. The formulas for resonance vary, and there's a couple of different ways to calculate your resonance. They have what are called closed tubes and open-end tubes, and they produce different resonance values, and there's different equations for those. I'm going to give you the main equation that you'll be using in here for resonance. But this is what you get when you have forced vibration, and then that forced vibration matches the natural frequency. This is what you do if you want to break glass. Have you ever seen these people that break glass with sound? Okay, there's a Mythbusters video clip out there where they take crystal. Now, you have to use crystal glass, okay? You can't just go home and pick any glass out of your cupboard and try to break glass, unless you just throw it down, then you can break it. But in terms of breaking glass with sound, it has to be crystal, like a quartz crystal. So these are like your wine glasses, right, or a champagne glass, usually thin, expensive. And when you tap those glasses, they resonate. Okay, they give off sound. That sound that you hear is the natural frequency of that glass. What you're trying to do is get a sound wave to hit that glass, and the sound wave is forcing the glass to vibrate. So that's the forced vibration part. Now, if you can get that glass to vibrate, you can match the frequency, okay, and get it to vibrate with that natural frequency. So you have to get a sound that matches that of the glass. So usually before somebody goes to break the glass, they tap it first so they can hear the resonance that they have, or the frequency that they have to match. And once you get to that point and you can hit that frequency with enough volume or loudness or intensity, at that frequency you can actually shatter the glass. Hopefully we'll have time, maybe on Monday, to show you that video clip in Mythbusters where they will actually break glass with the human voice. They have a singer that comes in and does it without amplification. No microphone, no speaker, just holding the glass next to their mouth and actually get it to shatter. Now, first of all, again, you have to match the natural frequency of the glass, and you have to have really loud, intense volume. So, but it can be done. There's ways to cheat, too. Now, when you hit resonance, you're going to get this huge, drastic increase in amplitude. And we're going to do this in lab. That's the second speed of sound lab that we'll do. It's pretty cool when you get to it. We're going to use resonance tubes, and you're going to use your tuning fork again. You're going to send a sound wave into your tube. So these are the setups that we're going to use. These big, giant graduate cylinders, just a little section of PVC pipe. And you're going to fill this with water. You're going to put your tube in there. take your tuning fork, strike it, send the sound wave down into your tube, and then you're going to adjust the length of your tube. And there's a certain point when you hit resonance that the wave going down matches the reflected wave coming back up. They become in phase with each other, and it gets really loud and intense. And you're looking for that point of resonance by adjusting the length of your tube. And it's obvious. A lot of people are like, how do you really know when you have the length of tube that you're looking for? You'll know. Because you'll hear that echo coming through, and then all of a sudden it's like, ooh, that's really loud from what it was before. That's because you got the reflected wave to match the original wave going down. That's your point of resonance. So that's what we're looking for. That lab is probably going to be on Thursday. So we'll play with resonance tubes. Let's see, formulas. We have this is an equation here now. Let me explain what this equation means. RS is resonance spacing. That's the spacing from wave to wave, from one wave to the next wave. Actually, I lied. That's your wavelength. Your resonance spacing is the length of your tube. Okay, so when you go to adjust your tube height and you're trying to find that point where it gets really, really loud, that's your resonance spacing. And then what you can do is you can use that number, the length of that tube, to calculate your wavelength. So resonance spacing equals, I think I have these laid out here. Yeah, resonance spacing equals your wavelength divided by 2, cut in half. So that's one of your basic resonance formulas. All right. Another one here is for open pipes and closed pipes. So it depends on if you have an open pipe at the end, because the waves are going to be, it's going to be harder for them to bounce back because you have an open end versus a closed end where it will echo off and come back. So for an open pipe, it's a little bit different. Just move things around. It's going to be your wavelength is equal to 2 times the length of your pipe. Or your tube, whatever you're using. Oops. So those are just 2 questions that might help you if they ask you about, okay, using resonance, calculate the wavelength of sound if the length of your tube is 0.5 meters, right? They're not real difficult. Now, how could this be helpful? Because once we know the wavelength, if we know the frequency, now we can calculate the speed. So by finding wavelength using resonance, it can help us calculate speeds as well. Because remember, velocity or speed is frequency times wavelength. Or if we know the speed of the sound, 343, then we can also calculate frequencies if we know what the wavelength is. So this is just another method that we can use to find those wavelengths. All right. We did force vibration, we did natural frequency, we did resonance. The fourth one here is fundamental frequency. And I know there's a question on WebAssign where you deal with this as well. Fundamental frequency is the lowest frequency produced by a vibrating object. The lowest frequency is always going to be your natural frequency. So that's where you start. All right, that's where you start. And then the multiples of that are considered to be your harmonics. Okay, harmonics are multiples, all right? They're multiples of the fundamental. So I'm going to go back to the tuning fork that I started with. Yeah, let's use a different one. Let's say I grab a different tuning fork this time, and the printed value on it is 150 hertz. All right, that is going to be the fundamental. right? It's the fundamental frequency, which should be equal to the natural frequency. They're going to be the same value. After all, fundamental means your basic, right? Fundamental means basic here. This is your basic frequency. Harmonics are going to be multiples of this. So we consider that your first one, your first harmonic. Okay, that's our first harmonic. Our second harmonic is going to be a multiple of this. So it's going to be 300 hertz. That's your first harmonic. Now here's a list to kind of show you what these look like. All right, so I'm using 50 over here. If your first, which is your natural frequency, is 50, then your second harmonic is going to be twice that. All right, so for this one, if it's a 150, then my second harmonic is 300. My third harmonic over here would be 450. On this example, if I have a tuning fork that's 50 hertz, it would be 150. It's always a multiple of the fundamental. All right, and then 200, and I don't know if I have a fifth one here. I don't. All right. Over here, it'd be 150, 300, 450, 600, and so forth. And I'm positive there's a question on WebAssign about this in terms of what is they ask for like what's the fourth harmonic of the fundamental frequency of a tuning fork with so many hertz. Just go 4 times whatever that number is. It's easy. All right, so these are your harmonics. All right, so that takes care of those 4 terms. Now, the last item here is probably the hardest of the equations that you have on your list for this chapter. All right, and it's called the Doppler effect. All right. Now, Doppler effect takes into account not only the movement of the sound, but also the movement of the source producing that sound. And the easiest way for me to explain this is to just give you an illustration. If a fire truck leaves a fire station going to a fire, and we're outside in front of the school, will we hear that siren when they leave the fire station? Yes. Okay, we should hear that. Now, can we tell, if we listen closely, can we tell if that fire truck is moving toward us or away from us? Can we tell when that fire truck turns, even though we can't see it? Can we tell when it turns direction? How do we know? What do you notice about the sound that's telling you that it's changing direction? What's increasing? You're right. Okay, the loudness and something else is changing that you notice. The pitch. The frequency is changing. Another example, well, let's just stick with the fire truck for now. So let's say they're coming towards us down Wayne Street. As they come closer and closer, as they approach, what you're going to notice is there's this huge increase in the pitch. It's going to get higher and higher and higher pitch. And then all of a sudden it'll come into our vision, we'll see it, and then it goes past us on Wayne Street, and then as soon as it gets past us, something else happens to the pitch. What's it do as soon as it goes past? It drops. It's kind of like what the tornado sirens do on the first Saturday of every month at 12 o'clock. Those tornado sirens sit on a pole and they spin, they rotate. As they spin and it comes towards where you're located, the frequency goes up, the pitch goes up. The intensity goes up too, it's going to get louder. And then as it goes away, it drops. And it comes back towards you again and it gets intense. And then it drops again. It's changing because the object producing the sound is moving as well, which is creating a change in the observed frequency that you're picking up with your ears. Show you this example here real quick. Car horn. Maybe. All right, so here's a car down the street, and it's going to be approaching the camera here. Hear the drop? coming. I mean, they didn't lay off their horn. They don't have a different horn, but they're approaching. It's getting intense, and as soon as they get by, then it drops. Same thing. And it's because the sound wave keeps moving, but the source of the sound is also moving. Oh, that's classic. You ever see a Big Bang Theory where Sheldon dresses up like the Doppler effect? We're not going to watch that, Mason. All right. All right. There's one with a train, but you get the idea. There's Sheldon. Never mind. It's only funny if you've ever seen the Big Bang Theory. All right. So here's what we get. When an objects separate, okay, when objects so they're moving away from each other, farther apart. What's going to happen is your frequency is going to drop. It's going to decrease. This is called red shift. You may have heard the term red shift before. Anybody ever heard of red shift? We have something called cosmological red shift, which says that our universe is doing what? It's expanding. Everything's moving farther apart. That's the same thing here. When things separate and they move farther apart from each other, you get what's called red shift. We will revisit this again when we get to light and color, because we get red shift again there. And it kind of gives a better explanation why we refer to it as red shift, why a color. Now, when objects approach each other, frequency is going to increase, because you're actually combining speeds. Not only is the speed of sound coming towards you, but the object is coming towards you as well, so it's coming at you faster. So your frequency is going to increase. This is called blue shift. So red is away, blue is towards. Red shift, blue shift. All right, and then here's just a diagram to kind of show you this. Here's red shift. Like when the sun moves away from your eyes, you tend to get red tints, okay, a red tint. That's why we refer to the color here. When you're moving towards something, you tend to get blue tints. Okay, you get a bluish tint to things. Now, that doesn't mean that, when green light's coming at you, it's going to look blue. It changes to blue. Now, it may have a bluish tint to it. Right? That's just something that it's a phenomena of the Doppler effect when waves are moving towards or away from each other. All right, here's the equation. It's ugly. All right, it's ugly. But it isn't that difficult if you follow some clues that we're going to give you here. A lot of variables, pluses and minuses, all kinds of stuff going on here. FO is the frequency of the observer. That's you. What are you going to observe in terms of the frequency? So this is you. FS is the source. That's the object producing the sound. So it would be like the fire truck, or the car, or the tornado siren. Now, there's a lot of V's going on over here as well. The regular V, the first V in the numerator and the denominator here, has no subscript on it. This is just the plain old speed of sound. And there's no temperature given to us here, so we're going to use what number? 343. 343, that's the value that we're going to stick in here for V. 343. Now, we've got VO and VS. That's the velocity of the observer. How fast is the observer moving? And VS is how fast is the source moving. We have to take the relative speed into consideration here. Now, when do we use plus and when do we use minus? That's the other catch, probably the biggest catch. When do we use plus and when do we use the minus? What we're going to do is we're going to combine these signs. We're either using the upper signs, the upper, so the plus here and the minus here, or the lower, the minus here and the plus here. And here they are. We use upper signs when the general direction is they're towards each other, and you use the lower signs when they are away from each other. Now remember, I give you the equations on the test, so you'll have the formula, you'll have the equation, but you're just going to have to remember these little parts that I put down at the bottom. When do we use the upper? When do we use the lower? And you have to know what the variables mean. But the equation will be given to you. You'll have that.
Teachers, pardon an interruption, but I need the following students for an attendance check. Cade Armstrong.
Tomorrow I'll give you one
Zachariah Shin,
example, practice problem that you can take with you,
Jacob Evans,
and we're going to do our lab tomorrow. So we're going to use the big giant PVC tubes. We're going to use echo to calculate the speed of sound. Yes. That. Hey, good news, we're done. No more notes there. We got everything. Everything we need for Unit 1. Good?